Welcome all the vendors to the Disruptive Technologies panel. We appreciate you taking your time to share some things with us. And just to let everyone know how the format works. And we do try to change the format of the user forum meetings, the structures and that. And we tried this at our April meetings. We're going to try it again. So we're going to ask each vendor is to keep their comments to 5 minutes. And then after each vendor talks about their disruptive technology, we have a set of panel members up here from the steering committee who will be asking these 3 probing questions of each vendor's presentation. And the questions are, is it really a disruptive technology? Who will likely be able to use it? You know, how broad is the market for it? And then also in the spirit of the user forum and collaborations and that, what can be done to bring it to market sooner? So those are the basic questions we have.
I just have to say, listening to the last presentation, which thank you, was very, very good. One thing that impresses me about HPC is that a lot of people don't realize what it does for us in normal day-to-day living, or what it does for us to actually protect us, give us the opportunity to develop, be in business, do things that influence people in their lives. A lot of those devices and planes you saw caused me to think of an experience I had last night at dinner. One gentleman came, sat at our table, and said, I had no idea that Altair does blah, blah, blah. And I kind of looked at him and I said, you didn't know that? And he said, no, I had no idea. I figured you guys were just HPC scheduler, a job scheduler. That's all Altair is. I could ask how many of you think that, and I'd probably see a lot of hands. Altair, actually, 95% of our company does all types of mechanical engineering, CFD, CAE, PD. We do all kinds of things. We have over 5,000 clients around the world. We have over 2,000 employees that are engineers, they're developers, they're scientists, they're innovators. And many times, because we're that kind of people, we don't do a lot of marketing. We don't stand up and tell everybody, wow, we helped build such and such, or did you know that part of our product was used on the SLS? So I'm going to very quickly just thumb through these, and hopefully this will work. You don't need to know anything about Altair except that we keep growing quietly. We're in 45 offices in 22 countries around the world. And the one thing about Altair is that we actually build the stuff that our clients use. And so we think like our customers. So in the market space, many times we're the ones who actually are using and experiencing the same problems that our clients do. So we think about that. This is a picture, I don't think anybody's seen this. This is in our headquarters in Troy, Michigan. It's kind of a cool building. It's actually built in this triangular logo that you see for our name, but people all over the world, we meet here frequently. It's a fantastic place to be because we're solving problems. The core of our business are these types of categories for software. Everybody thinks of Altair in this event with PBS Works right here in the middle. That's where I am. But everything else you see out here with partner alliances, cloud solutions, our HyperWork tools is where we do a lot of engineering simulation and performance optimization. Solid thinking, we now have a set of tools that can even accelerate that engineering process so that you can save money in designing. I'm thinking of one of our customers now that doesn't have to crash airplanes to find out whether or not it has safety protocols in place. They can do it through high-performance computing analysis. We also have a ton of services. We actually have engineers on site that are hired by many of our clients. And they use the tools that we write, and we use the tools that they need, and it works out well. We have centers of excellence. We do product design, human-centered industrial design with Think Labs. It's just amazing to me everything that Altair does. When we build software, our software really in the high-performance computing world can be divided into these 3 segments. The end user, of course, the actual efficiency of the systems and the resources that are used, and tools now to actually help IT management and decision makers decide whether or not X amount of licenses should still be used, or should we pay maintenance for that? Or do we really need to buy a bigger system? We have all of these tools wrapped into a package we call PBS Works Suite. Last thing we did 5 months ago in Tucson, we announced that PBS is now open sourced. It's true, we call it PBS open source. Oops, sorry, that thing is very sensitive. So if you wish to have PBS running in your environment, you want to take care of it yourself, you can do so. If you want to buy support and have us assist you in using it, you can do that. And we have a very flexible model to help you accomplish that. But we know that PBS is something that is important. It's been used in many of the companies who have made presentations here at this conference. And you can read that slide, but if you're interested, let us know. We have a lot of people who are already using it in this fashion. I think one of the thing I do want to point out, though, and it's on this last bullet here, we are an Open HPC founding member. That's important. We have a gentleman here who manages our partners and our relationships with them. So again, this we've done, we've delivered it, and you can get it. Just let us know. This is probably the last slide I'll show, and this is a great announcement. Many people are afraid of the cloud. We all know that we understand that moving data in and out of remote locations can be very troubling. So we were actually approached by UNLV and another supplier to provide what we're calling a ubiquitous cloud offering where you actually can determine all of the components inside that cloud and what you want it to be so that you can run your jobs, you can complete your work, you can do everything at the price point that you want. So we're proud to be connected with this. And that's it. That's all I've got.
So you covered many things besides disruptive technologies there, and we asked all the vendors to focus more on the disruptive technology. So is the disruptive technology you're referring to is making PBS Pro open source?
That's one element from the HPC side. The other thing, though, that is disruptive as we interact with companies is that they, many times, for business reasons, don't have the resources to go buy or upgrade their hardware. We have many companies who approach us and say, do you know a good place where we can make our environment exist within either a co-location facility or another environment that we can control completely? And we have the opportunity to do that now. We can also price point it so that it makes it easy for them to do their work. They don't have to wait, and they don't have to pay for inefficient system resources that were used to generate their results. They can actually select what they use as a resource. So that's disruptive. We have a lot of people who are excited about that.
Okay, so I asked the steering committee then to do the probing.
Well, I'd ask, what do you see as the market for this last product that you just have introduced with UNLV?
Well, I think it's interesting that when UNLV came to us, they described 3 different regions where they wanted this to exist. So these are the market segments. One is they want to create a Western corridor of research where all different types of universities can come and execute and do their work. That is expanding. We have many universities that either at no cost or just a little bit of cost, they want to be able to run their jobs in those environments. That's important for them, especially in our economy as it is today. That's expanding. The second area is that we have a lot of companies, both commercially and private held, that also want to control their expenses so that they can participate in that environment and control what's produced, how they get data inside and outside of it. Sometimes they need a bigger pipe. Sometimes they only want a pipe for a certain period of time. There's one particular customer in this environment. I can't give you their name, but they rendered the last 3 minutes of a movie in a specific area inside of this complex that you've seen a picture of. And they were able to do it and meet their timeline. So the flexibility of the resources and making them available to accomplish their need, that's a big thing. That's really big. Does that help?
Yep.
I think the other thing is that we have many other companies who do want to use PBS in an open source environment. We don't want that to become like every other open source offering that's been out there. Altair has spent a lot of money and will continue to spend a lot of money to support the entities who want to help develop the product and use it in their own space. So our support structure to make sure that this stays active is very important, and that's key. So that's critical too.
All right, so, you know, SUSE is doing open source operating system on enterprise Linux. And with an enterprise Linux, the OS, we have a big challenge because you need us to run a cluster. At the same time, you don't like us because every cycle you spend on the OS is a cycle you can't spend on your computation, right? So, and we are not looking into cool silicon technology or something like that. We are not people doing the next generation of computing or something like that. Our goal is more to look into what we can do to help the business to make it easier to run, right? And
You can go forward. I'll take care of moving it forward.
okay, one forward, please. So, and that means we are looking into where we can change the thing, how it is worked today or last year to make it into the future, have a transition. I call it disruptive in some way. It's not disruptive technology, it's disruptive business, of course. So we have to answer customer challenges, and you know all of this, I don't need to read it for you, and we have to answer, one slide for, and we have to answer a couple of market challenges. And I think the market challenges, we have heard about a lot of these stuff with an executive order last year or so, which people address. And we really need to work on all of these plain and easy to give more customers a chance to use HPC than it is today. It's cool to talk to many customers in this round, but most of you run big clusters, have big teams to make it happen. We are talking to business customers, they have just some admins, yeah, not well educated on HPC and want to make it happen. So there's a huge difference in it. Next slide, please. So what we changed in the last months, so, and I would call some of this really disruptive, is if you look on these boxes, a year ago, I was only capable of showing the left two boxes. And we changed it to get more stuff into it to get a focus. Next slide, please. Let me go into this. Oh, you have a second clicker, okay. So, one thing what we introduced or will introduce with SUSE Linux Enterprise 12 SP2 is an HPC module to give us a way to focus on HPC needs. And I need your help, your feedback. What do you want to be an OS vendor to deliver with an HPC module as part of the OS? So what helps you to make it easier to integrate, like hardware partners to do their own stuff on top or so. And that will, our way to focus on the specific life cycle of HPC, for example. Next slide, please. Another thing, openhpc.community. Many of you heard about it. It's a part of many discussions around. So we are founding member of it, and we are really proud of it because, by my view, it really changes the game. We are moving from many, many stacks to a few stacks, and that will help us as a OS and support partner to support a stack, right? It's pretty easy to make it to use our technology to give you a stack if we have a common ground. If you have to support a couple of hundred of packages, that doesn't work anymore, and we can't do it. Next slide, please. So, of course, cloud and HPC is a topic. We have heard it before. So, and finally, there's a partner we are working with that is Microsoft, and Christine is in the room, by the way, say hello, who is the alliance manager on the SUSE side for this, so ask her for any deep details. And Microsoft offering HPC in the cloud, and that's a great thing to work with, yeah, and we see many smaller customers, mid-sized customers entering the HPC market this way because they can't afford to create a room of systems or so. They can leverage the cloud for an easy entry into the market, and then they might build their own cloud later. Next slide, please. Another thing we announced recently on the ISC is a cooperation with Intel on the Intel HPC Orchestrator, which is a cool thing, of course, because it gives an enterprise-ready stack, ready to order, ready to install and use. And all of you know how much work it is to install HPC and keep it running. So, and that is really a game changer to make it turnkey ready and help you to make it happen. wide. So one slide, another slide, please. I might invite you to SUSECon. Just look at it. As usual, there's a discount if you use these stuff. Ask me if you want to take it. And else, we will see you on supercomputing again. Thanks. So, your questions?
And then questions in the steering committee?
Do you actually think this is more disruptive, or are you just creating more partnerships to forge your roadmap further in terms of growth for your company?
So the answer is both, of course. So everything what we do, or I approve as a product manager, I do because it helps our business. Because if it doesn't help the business, it makes no sense for us to make it happen. If you look into this, and in special OpenHPC and the partnership with Intel, really brings a big change, and that I would call a disruptive thing, right? Because if you think about a traditional top 10 site, how much is the lead time to set the system up, alone the time for the bits, for the public bits, yeah? And now think about a commercial customer, which might be not Boeing or so, but some smaller customers. Do they have the time and money and resources to run a 2-year proof of concept? Simple answer is no. They need something to order, to get next day and run it then, right? And today, a lot of HPC systems every system is different. And I acknowledge that we need these leading edge systems. We need these research systems to do really new cool technology, because this new cool technology will be standard technology a couple of years later. So by a business view, I think that is a big disruption. Even some of you in this room might not mention it because you run it in a different way than a commercial customer.
Thank you.
Okay, I'm Eric Van Hensbergen. I'm the director of HPC at ARM. I work here at our design center here in Austin. So just quickly, because there's not a lot of time, ARM, for those of you who don't know, we are an IP company, so we don't build chips, but we design chips and others build them. So our licensees include folks like Apple and AMD and Intel now, which is kind of weird. But so while we don't manufacture things, we do the designs behind them, and not just the chip as a whole, but the piece parts of a chip. And that's sort of where sort of the nature of most of the disruption around ARM is actually, again, sort of a business model disruption, in that we're not trying to force everyone to a single processor or a single type of system. We're actually, the disruption that ARM's providing within the HPC and the data analytics ecosystems is we're reintroducing diversity. When I started out in HPC while I was still at IBM, during the DARPA HPCS project, you know, there were I think 10 companies initially involved and several different architectures, and now we're getting down to, depending on how you count, 2 or 3 architectures competing in HPC, and ARM is trying to reintroduce diversity back into this ecosystem. And we do that in a variety of ways. From our business model perspective, we license designs for the cores and the different system components, and we also license our architecture. So some of our partners do their own microarchitectural implementations. And so it introduces a lot of different diversity in the way that the SOCs end up being designed for different market segments, which has given a lot of diversity in the mobile market and the embedded market and the networking market. And we're now moving into server data analytics and high performance computing, and we're hoping to do that there as well. So why is ARM interesting in this space? We were pulled into HPC, at least partially, for this flexibility that the ARM business model provides, but also because ARM has sort of a history of being highly energy efficient, which is increasingly important in high performance computing and in data centers in general. And so this has been sort of one of our core competencies, and it's what we're trying to bring both to the HPC market and the server market. And the flexibility one's a really interesting one. There's been a number of projects like the HPC for SOC stuff that a lot of the DOE guys have been behind that have really been trying to look at how to leverage this flexibility in the business model to increase diversity. From And so we're sort of deployed internationally through different partners in different areas. Within the U.S., we've been involved in the Fast Forward program together with our silicon partner Broadcom and Cray as a system integrator. In Europe, we've been involved in several programs, including the Mont Blanc program that's been going on for several years, looking at deploying energy-efficient SoCs in high-performance computing. And yesterday, you heard from Ryken about the post-K machine, I'm sure, with the Fujitsu. It will be based on ARM. And there are several partners in China that are also pursuing HPC-shaped machines. So from a disruptive technology standpoint, at Hot Chips a couple weeks ago, we decloaked our new vector extensions, which are specifically targeted at HPC. And so traditionally, we've had SIMD in the form of what was called Neon. But as we were moving into the HPC market, we wanted a much more aggressive computational story around vector computation. And so we worked together with Fujitsu and with Cray to help design a new vector extension to the ARM architecture to improve upon this. And we've also been working together with the Department of Energy through Fast Forward on this as well. And so what we came up with was this vector length agnostic architecture so that wow, there's a lot of builds on the slide, I'm sorry. Came up with this vector length agnostic architecture so that we wouldn't have to redefine the instruction set every time we decided we need a longer vector. And what this allows us to do is deploy a single ISA all the way from embedded through high performance computing. And depending on the specific implementation that our partner chooses to adjust, the same code can run across those in sort of a straightforward way. And this is disruptive in and of itself because it means that code porting can be much easier. And we're hoping that, and what we're seeing is that not only is this interesting inside high performance computing, but we're also evolving this architecture to be targeting machine learning and data analytics and networking as well. And I'm almost out of time. So just because everybody else mentioned it, we're also involved in OpenHPC. We're a founding member. And we're 80% of the way to fully building the OpenHPC packages with just about 2 weeks worth of effort. So we hope by supercomputing to have full continuous integration, and we'll have full OpenHPC support. So that same common platform will be available on ARM just like every place else. Questions?
So if I can ask the steering committee to do the probing.
Well, not so much a question, but a comment. I guess back in 2002, I was a recipient of a machine that, in a way, was somewhat like this. It was a Cray X1, which was, the chip was fabbed by IBM for Cray with a Cray custom vector unit. And that machine was a very innovative, disruptive technology machine, unfortunately short-lived. But I think this indeed, what you're venturing on, could be a very disruptive technology in the HPC arena.
Yeah, we hope so, and actually a lot of our collaboration with Cray on the subject stems from some of their experience in building those machines. And they've been quite useful, not just in giving us some of their wisdom of building big vector machines over the years, as indeed has Fujitsu, but they've also brought to bear tools that they've had for targeting these machines. And so I think what we've seen in our Fast Forward program is that that's allowed us to move much faster towards this and really sped up our adoption cycle on this. And we're seeing a lot of interest in this across the partnership, not just in HPC, but in other markets as well.
Do you expect any major changes in the acquisition from SoftBank?
This is one of the things that's going to make my marketing people upset that I'm up here talking about. No, so the answer is, so the short answer is no, not necessarily. This is our first week post-acquisition, so we're still finding out ourselves. However, what we've been told is that it's business as usual in all of our ongoing projects. The SoftBank acquisition will actually increase investment in certain areas, and that's really going to be the main way that they're going to change things. They're not going to cut off older projects or change our business model, but they're going to be investing and allowing us to reinvest in certain areas, and I expect actually with the public statements have focused a lot on IoT and big data, and so actually we are going to see more effort in those areas and in machine learning and so forth. So existing ARM models and projects is all going to be the same, but we're actually going to have much faster growth now in these areas of analytics and IoT.
Any other probing questions from the steering committee members?
I was just going to ask, so you might be aware that we've done some work with ARM in the past, with HP Moonshot especially. How soon, because that's one of the questions, how soon are you going to be able to bring some of the new hardware to your partners?
So the vector architecture that was described has actually been in partners' hands now for a while. So it's really a question for them in some ways. And it depends on implementation and partner to partner. But we are expecting, typically for partners, it's only a 2-year cycle from when the architecture is released to you start seeing products on it. But we will see.
Okay, thank you.
As far as disruptive technologies, well, first, I'm Bill Brantley. I'm in AMD research, and we've been working on the Department of Energy Fast Forward and Design Forward projects for 5 years, 3, 4 years, I lose track. At any rate, so I have a long-term perspective of what will be disruptive and a shorter term. So I'm going to sort of expound on this. For the longer term, I believe that the energy efficiency and the performance of SIMD calculations as embodied in GPUs is really has to be the future for computation. But with that, you need really tight coupling to traditional cores, and that needs an in-system fabric, network on chip or network on in package, whatever. And the GPU and even CPUs for HPC are voracious, have a voracious appetite for memory bandwidth. So the shorter term thing is high bandwidth memory or in-package memory. I'll get to that in a second, but in addition to CPU cores, which IBM has good IP, intellectual property and designs, and CPU designs for compute, which again, that's one of AMD's main product lines. You need a way to tie those together efficiently, not only at the hardware level, but in software, so that it's programmable. And we have our initiative with HSA and now ROCm, our evolution of it, which are open software systems, APIs, including the code for the compiler and the drivers and everything, is a differentiator and disruptive, allowing many more people to contribute to it, to the effort. Now, I think those are the longer term. Let me drop back to high bandwidth memory. This is disruptive, and last summer, 1 year ago, AMD introduced the first product that uses high bandwidth memory. It was a GPU about that big that has 4 stacks of high bandwidth memory. It achieves 250 gigabytes per second in the package. The next version of high bandwidth memory will be double that. So it's compared to what you can get from a traditional memory system. It's it's enables far more effective computation. So so I don't have to. All right. So that's the disruptive. I'll answer the rest of the questions as we go forward.
Great. So the steering committee, do you have any probing questions?
When will we see it in product?
Which HBM?
In HPC systems.
In HPC systems. I think it'll first appear in GPUs, and it's already in a product, but it's not. It's more for graphics and gaming. It turns out, though, that product is really good also for for machine learning because they use short precision. The particular, for gaming, you don't need good double precision. So it works on single precision or sometimes half precision floating point. This unit has good, very high single precision. So you're already seeing the benefit of it, and I think over the next year or so, you'll see mass adoption. And this breakthrough, it's taken almost a decade. It's not just stacking the chips, it's the whole manufacturing process to allow you to have high yields. So it's, it's taken, it is disrupting, and we're just seeing the beginning of the wave. Anything else? Yes.
When I think of a disruptive technology, I think of something that puts other people out of business, right? It replaces them. Or it introduces something that no one thought they needed, but now everyone can't live without.
Mm-hmm.
How would you characterize this? Which of those? Which of your colleagues are you going to be putting out of business, or, or are you just something that everyone's going to go, wow, we never knew we needed this. Thank goodness somebody thought of it. We can't live without it.
Well, as much as I'd like it to be unique to AMD, it's not. It's memory for something at this, some technology like this. It has to be available universally because there's a high cost to adoption, but then there's a high benefit. So I think you'll be seeing it in other GPUs from other companies, and I believe that Xeon Phi has, that it's not the JEDEC high bandwidth memory, but they have another stacked memory technology in there. It's just our need for bandwidth is accelerating greatly as we get higher density compute. And so it's going to, I don't think it will become ubiquitous, but it might. If you could get enough memory with your laptop, you could have, a one package laptop part. So that may count as ubiquitous, but, so anything else?
I'll just stand over here in case I wave my arm and don't hit this gentleman in the head. So the number one question I always get is, who is Ryft and what do you do? Right? Because not many people know about us. I see a lot of familiar faces. I've seen a lot of you before at a few of these shows. And IDC has invited me to talk a couple of times about some of the stuff. And they often say that we're disruptive technology, but I actually believe that disruptive technology is in the eye of you. You decide if it's disruptive for your market. We are not an HPC company. We are an HPDA accelerator. We accelerate data analytics. That's our whole purpose for existence. We've done it with the intelligence community for about 20 years in various capacities, and we've tried to take that technology commercial. One of the questions that was asked initially here was about adoption. I'll touch on that in about 2 minutes from now, but I think that's really critical, is how to drive adoption of new technologies, whether they're disruptive or not, because even a non-disruptive technology can add to your toolbox. So that's what we do. We accelerate high-performance data analytics. Why do we do it? Because we're using the wrong tools for data analytics. We're trying to leverage what we know about computational science for big data without thinking about what that means. That's a mistake, and we should realize that and not fight over it, but just accept it. Here's why it's a mistake. Here's why I know that's true. Because today we have all of these issues. We take too long to extract, transform, and load data in order to index it, in order to process it, and make no mistake about it, even using many cores, you're still sequentially processing data at some point with a sequential instruction set, which, by the way, is now running at lower clock speeds, because we can thank Moore's Law for that. And so this gives you all these analytics bottlenecks, not the least of which is because of all these red lines in the network when you're transmitting data all over the place. So when we decided to bring this technology out of the intelligence community and into the real world, so to speak, we figured, okay, we need to figure out how to make this whole thing easier to use. That's the disruption we bring to the table. Yeah, we're really high performance. We have some ridiculous numbers. We can just prove them to you by showing you a demo like we did for a couple of you already today. We just show you, we don't tell you. But the real reason we are disruptive is we make it easy to use. We've talked a lot in this particular conference, and I liked it yesterday, about education, the education problem that we have. How do we train people to use these technologies to solve these difficult problems in the era of big data? And we talk about new course curriculum, and those are all excellent things, and I applaud everyone doing that work. That's great work. That is needed work. But what if there was a way that you could use existing trained computer scientists to do that work? We know how to do that. We've fought those battles. We've learned those lessons. We failed going to market once before because we didn't take that into effect, and we take it into effect now. What does that mean? Well, I'm going to skip over the box, and I'll talk about that later. You can come talk to me about the box. We're going to talk about disruption in the space. What this means is I have to figure out a way that I don't have to do ETL or indexing, that I don't have to do traditional parallel processing techniques, that I can use standard Java programmers to write code and get good results, because that's how they're trained in schools, whether we like it or not. One gentleman earlier said, it's my job, it's our job collectively to figure out how to solve this problem. Well, if we have to train kids coming out of school to do this the right way, that's 5, 6, 7 years for getting a PhD before they can come and work for us. That's unacceptable. I won't be around at this company in 7 years. I got to wait to hire them. I got to do it now, right? And so what we've done at Ryft is figured out a way to collapse a lot of this stuff into a single node. My favorite parable is if you have a hurt, your shoulder hurts, right? And you go to the doctor and you say, doc, if I got to, whenever I reach back like this, my shoulder really hurts. And what does a good doctor tell you? Well, just don't do that. I mean, why on earth are you going to keep doing that if it hurts you? And that's the same thing with HPC applied to HPDA. Don't let the network be your bottleneck. Keep your data local to your compute, if you can do it. And it turns out in the commercial space, you can often do that because you can keep your data sizes manageable. In that single 1U Ryft 1 box that we have, we can support 48 terabytes of simultaneous data access. In 1U. Think of all the data savings you compare that to a 48 terabyte in-memory database system. 2 full racks of equipment, God knows how much power, IT support, real estate, it's insane. And when you then couple that into using this at the edge, in the cloud, or in a local node, there's just no another way around it. That allows you to be disruptive because you can now use standard programming techniques to run these things with standard interfaces. And that's what we do at Ryft. We have FPGA-based technology for the compute, high-speed SSDs for the storage, local interconnect on the fabric, and we abstract all that hardware away with standard Linux APIs. So anybody, even the Java programmer coming out of school tomorrow, can make use of it and get high performance right now. That's why we're disruptive.
Great. So does the steering committee have some probing questions?
Under full disclosure, we are piloting one of your boxes and with great success.
Thanks,
how will you bring this to a bigger market, which is obviously good for everybody?
I am extraordinarily pleased that you, of all people, asked that question because you are using one of our boxes. And that's how. People in this room are the experts in what we traditionally think of as high-performance computing. The way that we get the market to adopt these things is to talk about them in open forums, right? The problem we have at Ryft as a small company working with and there's a few other people in this room that we are working with also, under strict NDA as well, which is why I haven't mentioned them at all and will not. We have to be able to get beyond those NDAs so we can talk about it and talk about why we're using this technology, how it's being used, and how it's making a difference. And until we can do that at a larger scale and publicly, the adoption is a big problem for us and for everybody else with disruptive technologies on this panel and in the room.
I guess we have a question back here from Jay.
How is this fundamentally different from what Conway tried to do?
That's an excellent question. In a way, we were Convey at one point.
So for those of you who don't know who Convey is or was, I imagine most of you probably do in this room, they had FPGA-based PCIe accelerator cards that they used to sell on for existing servers. That was their problem. They sold accelerator cards. We used to do that too, by the way. We had a board that we called the FMP. It's called a flash memory processor. And it failed horribly in the commercial segment, did fairly well in the government. What they did wrong was they neglected the ease of use part. They didn't realize their strength wasn't that they were using FPGAs. Their strength was that they had the ability to implement very difficult algorithms in FPGA that the end user wouldn't have to implement themselves. And that couldn't with traditional technologies. Because FPGA, my favorite example there, it's like an Etch-a-Sketch. If you're familiar with those old school tools growing up, right? You can literally shake this thing up and draw something new, and it works just like you drew it. You can't do that with CPUs or GPUs. You're confined to an architecture. You can't do it with any sequential instruction set, but with FPGAs you can. Convey didn't capitalize on that. Our initial mistake was we didn't either. We thought our disruption was our FPGA heterogeneous computing use. It's not. Our disruption is how we make that so easy to use that you don't have to spell FPGA. And that's what they did wrong. And as a result, they had a fire sale and Micron bought all their good stuff. Apologies, my friend. Yeah, so just and also in full disclosure, one of our board members is a Micron executive. So he was involved in all this as well, and I'm not in any way bad-mouthing Micron or Convey. I'm just pointing out that it's my opinion that I believe that they did end up failing and having to sell at a much lower cost than they wanted to because they couldn't overcome this ease-of-use problem. And I think we all face that on a day-to-day basis. We have to figure out a way to get the masses able to use these technologies to solve commercial problems. And that is, in the end, an ease-of-use issue.
Thanks. I don't have any slides up, so I'll just talk about a couple things. So Red Hat, I mean, we're right now $3 billion and running open source company that's been producing a wide range of software stacks. We're not exclusively focused on the HPC market, but we enable a number of partners in the HPC space. So in terms of disruptive technologies, a lot of the conversations over the last two days has been around ease of use, you were just talking about that, and training people to enter into this market. And so one of the things that's sort of happened is as compute power on the CPUs is declining and people are using off-processor compute, whether in the GPU space or FPGAs, it is becoming difficult to understand how do you program those things. And then as you look at data sets, how do you access these data sets across the space uniformly? So one of the projects that we had started at Red Hat with a couple of our partners is a notion of heterogeneous memory management within the Linux kernel. And so the goal for us here is to say the memory addressing scheme that the kernel has is system-wide. Doesn't matter where your code is running, whether it's actually running on the CPU or in the non-CPU space, the programmer can address any memory in the system. And the system will take care of making sure your memory that's in use migrates to the device-specific memory. So whether the device is an RDMA card or whether the device is a GPU, all that should happen transparently, and that should ease the programmer's ability to exercise the system. When we started the project 2 years ago, when we first did the upstream posts on the Linux kernel list, it was interesting where everybody was like, why would you want to do this? This hardware doesn't exist that would support this. And we're sort of looking at now hardware that does support this actually exists. So some of the Mellanox cards will do this, and the GPUs are just starting to get to this space. So we're expecting in the next 18 months or 12 to 18 months, we'll actually see this hardware fully enabled in the open source community. and have this productized. And I think that'll change programming models for the developers and make this much more accessible. Because you don't have to now reduce the data set, transfer it to the GPU, and things like that. So that's probably the smallest piece of disruptive innovation that I see in the next few months.
Okay, excellent. And the steering committee, do you have some probing questions?
So I'm going to blend a few things together. From the commercial side of things, and we talked about the education portion of things yesterday. How do you see developers actually taking advantage of this hardware, programming the hardware specifically to match what you're building?
So a lot of existing techniques are there to program the processor side, right? So I don't think we've solved the processor side of the equation. So things like AMD's HSA and those tools will help in the processor side of targeting processors. What we've been working on is the inverse. If you are in different processors, how do you get access to the uniformity of the memory?
Great, thank you very much. And next we'll hear from Cray.
Hi there, I'm Bert Beals. I run the global energy industry, specifically the oil and gas business for Cray. And while I had some slides, I'm sick and tired of slides, so I'm going to let you guys not take a break from death by slideware for a little bit, and let's just talk. We could go on for days talking about fascinating disruptive technologies and spin the technology beanie propeller quite a bit on things that we're working on. I thought it'd be a little more interesting, at least my perspective, to talk about in summary some of the things that we've heard about yesterday and some things we've heard today, and to give you some real world particulars on changes that we're seeing, disruption that we're seeing in the way that people do their business, whether it be research or the way that they actually do the core parts of why they're in business. Wrap it around, I guess, about 3 different things that I see that are disrupting the way that they go and do that. One of them, we talked it to death. I'll talk a little bit more about some specific examples in the convergence of high-performance computing and analytics. So that's one thing that we'll talk about there some. Another is we don't like to talk about it because a lot of people worry about, well, what are we going to do with it anyway, is this absolute tsunami of data that's going on. And it's only getting worse. I mean, I talk to senior executives at oil companies that say, we've got more data than we know what to do with. Matter of fact, we've got data we didn't even know we had. So the questions of how do I deal with that, both from a high-performance computing perspective and an analytics perspective, is an issue that folks are dealing with that is truly driving a lot of the thinking about what they do with their infrastructures moving forward. And I guess the last thing to go on is some of the emerging technologies. We like to call them emerging technologies, the machine learning and deep learning and large graphs and streaming analytics and so forth. I did want to bring a little bit of real world to some of that as well, in that to some degree we need to stop calling it emerging, because we've got lots of folks that are utilizing all of those technologies in production today. And what we're not doing nearly as good a job of is getting the message out of what those benefits are of them actually using those radical new technologies. Especially the impact of their business, or the impact to their ability to do research, or their ability to go and foster new discoveries in ways that the human mind never would have thought of before, some of like what we heard earlier this morning. Just a couple of few things. This whole convergence of supercomputing and analytics, that's something we've been working on for years. We are customers at Oak Ridge and NERSC in the States, CSCS over in Switzerland. We've been working with them to augment some of their traditional HPC workflows by bringing in technologies like Spark and so forth in the supercomputing environment that a lot of people, their eyebrows raise up and say, you're doing what on a supercomputer? So it's allowing them to do things that they've never done before. Well, that's great. Those are great big facilities and so forth. How does that apply more to what near and dear to me, which is the oil and gas industry? We're actively utilizing analytics to optimize full waveform inversion workflows, for example, by providing the ability to do stochastic modeling and so forth as part of the workflow to help converge the models quicker. So it's this interesting converged workflow where parts of it are traditional HPC and then parts of it look more like statistics in order to be able to reach a resolution quicker. Some of the more interesting research things we're working on are doing things like using analytics on 3D wavelet analysis to provide better code quality on the input to seismic processing workflows. Another really fascinating research project that we're working on that we've been doing using a bunch of time over at NERSC is combining multi-physics approaches such as reservoir simulation mixed with 3D geomechanics and rolling into that the analytics capability of looking at things like logs or applying stratigraphy where we're doing fossil identification and wrapping all of that together to provide the business with a better simulation of how their reservoir behaves or help them understand how better to optimize and manage that reservoir to either increase production of hydrocarbons or make that production more efficiently, which is incredibly important right now given where we are with the price of oil. So I'll close up mostly there. The application of this is broad. It may surprise you to know, I'll close with some of this. We're actually working with some of the ISVs within the oil and gas industry that are completely retooling their seismic processing applications, which we traditionally think of as, yeah, that's real HPC. Well, these guys are using Mesos and Spark and Scala, and it just goes on and on and on in the next generation of what that looks like. And what that does to us, in closing, is it causes a change in everything we do, how we think about architectures, the technologies that we need to apply to building systems as we go forward, because these converged environments, along with the data requirements, are driving us to just totally change the way that we think about what platforms need to look like as we go forward. So it's almost an interesting thing about disruption. Things that are going on that we've been working on in the community are actually driving disruption for us, where we're having to change our business and the way that we do things to help continue feeding this feedback loop that's started now between this convergence of HPC and analytics. I'll stop there.
Okay, great. And steering committee, do you have some probing questions? Paul, you must have at least one question for Cray.
Well, I'm not sure if it's a question, maybe it's just a comment. You started off talking about how the very large-scale data is just, it's tumbling ahead of everybody, and we're having a hard time getting our arms around it. But then you shifted, and it sounded like you said there are a lot of technologies and tools you have now that maybe aren't being used quite as effectively as they could be, which kind of sounded to me like you've introduced disruptive technologies, but the market just isn't smart enough to realize it. So I'm wondering, and then you ended by saying we're coming together and trying to figure it out. So,
yeah, you exposed one of our Achilles heel there. We don't do a real good job of getting the story out about what we're working on, and supercomputing would be a great place to have those kind of conversations. But suffice it to say, there are pockets where we're applying technologies, designing and developing new technologies. You heard about Path Forward. You heard about some of the things that SUSE and Red Hat and ARM and AMD, all these folks are working on that are part and parcel of the R&D efforts that we do. But we don't do any of that in a vacuum. That's the part that gets that we don't talk about enough, is all of these things that we do, we're doing in conjunction with somebody. You know, it may be in conjunction with PGS in the oil industry, or it may be in conjunction with the folks at Oak Ridge or at Argonne, for example. But I guess the short answer is, yeah, it's kind of all over the map right now as far as who's being successful and who isn't, but the fundamental thing that it's doing to us is it's driving system designs that are being built to address those hurdles that we recognize. You know, one key thing, eliminate data movement. Oh my God, between HPC and analytics, I cannot be moving data sets anymore. They're too big. So the issues around how do I get these environments that to some degree have grown up separately from each other. You just look at the sprawl of Franken clusters out there, for example. How do I get those things to behave well with each other with common data stores? And how do I provide the radical difference in performance capabilities required by these different steps in an application workflow? And those are all the things that we're working on. Some places we're further ahead than we are in other ones. We're starting to release products that specifically address some of these. And if you sit down and we get a little bit of time in a roadmap presentation, I can give you a little more detail.
Diversity is a good thing, and all of these things are an evolutionary process. And I'll give an example of a presentation at a prior HPC User Forum, and that was in the area of linguistics, where some researchers from the University of Reading applied tools that were traditionally used in the area of genomics to linguistics. And this was a very different approach than people in the field of linguistics had previously used. And so generally in linguistics, they said you can trace back languages about 8,000 years, but by applying tools out of genomics, these people were able to trace back roots of language 100,000 years. And so what you're describing is that there's many tools, many different innovations, some spectacular, some not, but they all lead to disruption.
I completely agree. I like the point on linguistics, by the way. That's actually another example I didn't get to, was talking about the hawking problem, where if someone is unable to express themselves linguistically, how can I allow them to be able to communicate? And there's another project that we're working on to deal with that particular issue by applying, once again, HPC and analytics. You know, we could go on and on and on with examples. Personalized medicine's another great one, where we're starting to merge together some of the traditional things you see in protein folding and genomic analysis with patient history analytics and population analytics, and like some of the things we saw this morning, particulars on race or environment or so forth, and how those fit into how we treat particular individuals, not entire broad brush classes of individuals. So it's just more and more of that, and in the successes are starting to, like I said, cause a feedback loop to where this is accelerating. It is absolutely accelerating. It's disrupting pretty much anybody that wants to be competitive out in the marketplace.
So Bill Manel again from Hewlett Packard Enterprise. So I'll start the talk out with actually stating a problem, and it's interesting. We were talking about the challenges around data movement and how much data is out there. But if you look at this slide, I mean, these are actually leadership systems in DOE right now, even going out into the future. So these are systems in some cases that aren't even installed or in production yet. And what we see is a variety of measurement of bandwidth, of memory bandwidth, how much memory per CPU. And what we see in the trend here is that with sort of the more familiar bytes to flop ratio that I think a lot of us are familiar with in the industry. And what you see here is that over time, even going on to systems that haven't been deployed yet, you know, we're seeing that going down. So this data problem we're talking about, we're actually getting worse at as we go forward. So a decline in just about every measure of injection bandwidth, and so forth and so on. So what are some technologies to actually get us out of this current trend? So I'll talk about a number of those. One of the problems we have is that we're sort of chained to the past. So a lot of CPU architectures today are based upon the fact that they have to interface to a lot of really obsolete buses out there, everything from DDR to SAS and SATA and a variety of things. That's the typical complexion of the CPU or the system on a chip today. What we're starting to work on is a next generation memory interface that actually allows you to interface to the chip in the way you want to, and with a variety of different types of technologies in as well. So as opposed to using a lot of your pin count in sort of old things you don't care about anymore, this allows you to use your pin count on things like getting more I/O in and out of the chip from that standpoint, and getting more data and increasing that byte to flop ratio. So another technology is something we've been working on in HP Labs for a while. It's called our HyperX. And this is how we would build a topology for an exaflop type of computer. And in fact, this actually allows you to scale out into 6 exaflop and up to a 250,000 sockets in terms of size. So basically, we're starting to do work on developing a high radix switch and a set of topologies to actually drive this type of technology. So again, you can support up to 6 exaflops with a one-to-one bisection bandwidth. There's some a great paper on this that you can read as well that came out from HP Labs. Finally, another set of technologies is really around silicon photonics. So as we talk about exascale, what you really see is using today's optical technology, and this is just an example of a price of an optical cable today, and the amount of power it uses. What you see is that at an exascale system, you'd spend $1 billion just on the cabling and nearly 10 megawatts of power just to move the data back and forth. So we really need to up our capabilities in terms of silicon photonics, get us down. And so some work we're doing internally at HP Labs is to get us down to 10 cents a gigabit, and also 3 to 6 picojoule a bit from that standpoint. So a lot of technology work needed in terms of that. Otherwise, we just kind of fall over in terms of just getting our data moving around in an exaflop type system. And finally, the last set of disruptive technologies is really universal memory for HPC. So how do you basically bring all that memory together to be accessible across the machine, and also have the speed and the power usage that will be effective. So we've been working on a product called Memristor for a while, and so these would allow us to bring that technology together, and as we go forth, would be able to address some of these problems. And then finally, what we're projecting for, as opposed to this downward decline across these systems, is actually getting us up there in terms of much better ratios in terms of memory bandwidth and injection bandwidth and those things. Any questions, please?
Great. So any probing questions from the steering committee members? So maybe I'll start with one of them, and that is, to do this, you mentioned some really exciting new technologies.
Yes.
What do you need to bring it to market sooner? Is it funding? Is it more experts in HPE? Is it some partnerships with government labs or universities?
I think it's all of the above. So, in some cases, the technology has to develop. In some cases, it needs dollars. And in some cases, we need partners that are engaged, interested in driving forward as well.
Okay.
So.
Any other questions from the steering committee? Or the audience itself? Well, with that, I'd like to thank all the vendors here. I know it's difficult to be concise and compress everything in a short period of time, but I think you did an outstanding job.